You're not ordering pizza, you're triggering a machine, a system built to move heat, to control fermentation, to manage moisture, to compress time. A pizza does not arrive hot by luck, it arrives because variables were anticipated. Dough expansion, cheese melt behavior, cardboard airflow, driver route timing. At scale, dinner becomes engineering. Scale changes the rules. Domino's produces millions of pizzas every day. Millions. Across thousands of stores, across different climates, different humidity levels, different labor speeds, different traffic patterns. At home, inconsistency is normal. At industrial scale, inconsistency is failure. Dough is biological, sauce is chemical, cheese is reactive, heat is unpredictable. And the product doesn't end at the oven. It ends at your door, which means the system must extend beyond cooking, into logistics. The real challenge. Making pizza isn't hard, making it identical. At speed, everywhere is. If dough ferments too long, gas pockets overexpand, crust weakens. If fermentation is too short, texture turns dense. If sauce spreads unevenly, moisture concentrates. The center collapses. If cheese moisture rises, oil separates during baking. Grease pools. If delivery stalls, steam softens the crust from within. The oven can be perfect. The product can still fail. So Domino's doesn't just manage cooking, it manages time. The box that made delivery possible. Before apps, before GPS tracking, before digital ordering, there was cardboard. The modern pizza box is structural engineering disguised as packaging. Corrugated fluting between paper layers creates vertical compression strength. It prevents collapse when multiple pizzas are stacked. Air channels trap heat while allowing limited moisture escape. Too sealed, and condensation rains back onto the crust. Too ventilated, and heat dissipates too fast. Cardboard absorbs micro-condensation, but not enough to dry the product. The box solves a physics problem. How do you move a fragile, hot, moisture-releasing disc through space without destroying it? Pizza is not just food, it's a temperature-sensitive payload. Centralized production, the hidden factory. Individual stores do not mix dough from raw flour daily. Instead, Domino's operates regional supply chain centers. Industrial hubs, controlled environments, standardized production. This is where consistency begins. Because decentralization increases variability. Centralization reduces it. Raw ingredients arrive in bulk, flour by the truckload. Oil in sealed containers, yeast under temperature control. Every batch is measured, logged, tracked. If inputs drift, the system detects it upstream. Stores become assembly lines. The factory lives before the storefront. Dough, controlled biology. Dough is alive. Yeast consumes sugars, produces carbon dioxide, builds internal gas structure. But yeast doesn't follow schedules. It follows chemistry. Industrial mixers combine flour, water, oil, salt, sugar, and yeast. Torque builds gluten networks quickly. Gluten is structure. Without it, gas escapes. With too much of it, elasticity resists expansion. Development time is calibrated. Underdeveloped dough tears during stretching. Overdeveloped dough shrinks back. After mixing, the mass drops into automated dividers. Blades portion precise weights. Weight determines thickness. Thickness determines bake time. Bake time determines moisture retention. Each portion moves into a rounder. Surface tension forms a smooth outer skin. That skin traps gas. Gas defines crumb. Geometry influences performance. Chill, don't freeze. Fresh dough continues fermenting. Left unchecked, it overexpands. Freezing would halt yeast, but damage cellular structure. Instead, dough trays enter controlled chill rooms. Around 39 degrees Fahrenheit. Cold slows yeast activity without killing it. Fermentation pauses. Structure stabilizes. The goal isn't to stop biology, it's to delay it. Trays are spaced to prevent sticking as dough expands slightly. Robotic arms stack and wrap them for transport. Even spacing matters. Touching dough balls transfer moisture. Moisture alters surface texture. Control is layered. Sauce, balancing acidity and viscosity. Tomato paste arrives concentrated. Industrial blenders rehydrate it to calibrated thickness. Viscosity affects spread behavior. Too thin, and sauce migrates during baking. Too thick, and it resists even distribution. Salt sharpens flavor and preserves stability. Vinegar adjusts acidity. Acidity balances cheese fat. Without acid, fat tastes heavy. With too much acid, flavor becomes sharp. Herbs are measured precisely. Garlic, oregano, basil, pepper. Volatile compounds are heat sensitive. Blending temperature fuses flavor without degrading aroma. Sauce is portioned into standardized containers because a few extra grams per pizza scaled across millions becomes a supply chain disruption. Mozzarella, engineering the melt. Cheese is not decoration, it is a thermal reaction surface. Milk is pasteurized to remove unwanted microbes. Starter cultures are added. Bacteria convert lactose into lactic acid. Acidity changes protein behavior. Rennet coagulates casein proteins into curd. Whey drains away. Curd heats and stretches. Stretching aligns protein strands. Alignment defines melt elasticity. If protein alignment is weak, cheese breaks apart during baking. If too tight, it resists melt. Moisture content is critical. Higher moisture increases melt but risks oil separation. Lower moisture reduces grease but stiffens texture. Brining controls salt and moisture simultaneously. Blocks form, then shredding increases surface area. More surface area means faster melt. Even shred length affects coverage uniformity. Melt is not random, it is engineered response to heat. Pepperoni, time as a control variable. Pepperoni begins as ground meat. Salt stabilizes proteins. Spices define profile. Starter cultures initiate fermentation. Warm, humid chambers accelerate bacterial growth. Bacteria produce acid. Acid lowers pH. Lower pH improves preservation and safety. Time deepens flavor. After curing, slicing machines cut precise thickness. Thickness affects oil release during baking. Too thick and slices cup aggressively. Too thin and they dry out. Oil release interacts with cheese surface. Everything interacts. Nothing cooks alone. Store assembly, human motion within a system. Ingredients arrive refrigerated. Dough temp gradually rises toward elasticity. Too cold and it resists stretching. Too warm and it overexpands. Cornmeal reduces friction. Dough is stretched by hand. No presses, no rollers. Presses destroy internal gas pockets. Hand stretching preserves structure. Sauce is applied using a calibrated ladle. Circular motion distributes evenly. Cheese goes edge first. Why? Edges brown first. Center retains moisture longer. Balanced layering controls bake gradient. Toppings spiral inward. Distribution prevents center overload. Center overload traps steam. Steam softens crust. Physics dictates assembly. The conveyor oven, moving heat. Oven temperature hovers around 465 degrees Fahrenheit, but temperature alone doesn't define baking. Time does. Conveyor speed controls exposure. Moving belt ensures uniform heat distribution. Radiant heat browns cheese. Convective heat cooks dough interior. Moisture escapes upward. Oil melts downward. The bake is a controlled dehydration event. Too short and structure remains soft. Too long and moisture loss becomes excessive. The oven is calibrated daily. Heat is measured. Belt speed checked, because thermal drift compounds quickly. Delivery, the final variable. Once boxed, the clock starts. Steam continues escaping. Cardboard absorbs some. Air carries some away. Heat retention declines over time. Drivers follow optimized dispatch systems. Order batching balances speed and efficiency. Route planning minimizes delay. Because even 5 extra minutes changes crust texture. Delivery is not an afterthought. It is the final stage of cooking. Time is an ingredient. Final reflection. A Domino's pizza appears simple: dough, sauce, cheese, toppings. But behind it sits fermentation biology, protein chemistry, moisture migration physics, thermal engineering, corrugated airflow design, last-mile logistics. This is not just fast food. It is a synchronized system managing a living product under time pressure. The mixer, the chill room, the oven, the driver, all connected. Because at scale, taste is only half the equation. The other half is repeatability, and repeatability is control. Next, inside the Reese's factory, where chocolate becomes a precision shell around a flowing core, behind every familiar meal, there's a machine thinking ahead of you.